molecule. It's Lewis acidic, and a molecule or ion that accepts a pair of electrons. All right, so these are interchangeable terms, like Lewis acid and also a molecule of iron that accept a pair of electrons. They're the same thing. We also went over substitution, right? So the name of the reaction we care about is nucleophilic substitution reaction. We went over the definition of nucleophile and also what is substitution. So substitution is an elementary step in organic chemistry in which we're making a new bond while breaking an existing one. So if we're doing the arrow pushing here for this one, we're talking about formation of the new bond between A and B and breaking the bond between B and X. But if we think about what is happening in here, effectively we're making a new chemical bond between A and B. We're breaking an existing chemical bond between B and X. So naturally, one can propose two different reaction mechanisms for this substitution to take place. So that comes to the idea of nucleophilic substitution and the two reactions of interest. First, what is nucleophilic substitution? Well, we're saying a reaction is a nucleophilic substitution. We're saying a nucleophile substitute for another at a tetravalent carbon center. So we're looking at a carbon with 4 groups. In the general reaction, we're talking about the nucleophile, or abbreviated as Nu, with a lone pair. It can be anionic, it can also be neutral. And then on here, we have a tetravalent carbon. So carbon with 4 groups, so tetravalent carbon. And we have a leaving group. Right, so in this general reaction, the nucleophile replaces the leaving group on the tetravalent carbon to form another tetravalent carbon, and then your leaving group leaves. So for this substitution reaction, well, we have 2 mechanisms that are possible depending on the nature of the bond-forming, bond-breaking processes, or, well, whether or not the bond-forming and bond-breaking is concerted or stepwise. So here are the 2 mechanisms that are possible are called SN1 and SN2. So let's just go over what does each term means in here. The S stands for substitution. N here stands for nucleophilic. All right, so taking together, the SN tells us this is a nucleophilic substitution reaction with the general reaction scheme shown above. And then this 2 here is of particular interest. This 2 here stating a bimolecular. So the bimolecular means 2 species are involved in the rate determining step or rate limiting transition state. So RDS, rate determining step. So 2 species are involved in the rate determining step. So in this case, we only have 2 reagents, right? You have nucleophile, you have the tetravalent carbon. So both my substrate are involved in the rate determining step. So SN2 is saying we have simultaneous bond forming, bond breaking reaction mechanism, or a concerted reaction mechanism. All right, so that's the name of SN2. Alternatively, we have SN1. Same logic, S stands for substitution, N stands for nucleophilic. Now, my 1 stands for unimolecular. Or only one species is involved in the rate determining step. All right, so only one of them is involved. So stepwise bond breaking forms intermediate, and then the second bond is forming. So that's the general gesture. Let's look at the actual reaction mechanism of SN2 and SN1 and see what can we derive by observing these mechanisms. And then, after we went over the mechanism of SN2 and SN1, we'll talk about what are the factors controlling each reaction mechanism and how to decide when you have two substrates whether or not it's going to undergo SN2 or SN1 reaction mechanism. So getting started. SN2 mechanism, as its name said, it's a concerted reaction mechanism. So means we can have bond forming, bond breaking simultaneously. So if we look at the energy diagram, on the x-axis, that's my reaction coordinate from reactant to product. Y-axis is my energy. So in this reaction, what are my reactants? My reactant is my OH minus and my bromine methyl. All right, so these are my reactants. What are my products? My product are my HO, CH3, and Br minus. So in here, if we're identifying what are the names of my contributing parts in this reaction, my OH minus is my nucleophile, and my Br is my leaving group. Right. In this concerted pathway, we are breaking the carbon-bromine bond while forming the carbon-oxygen bond. So if we're drawing the transition state out, it will look like this. So we have a partially forming oxygen-carbon bond, and a partially breaking carbon-bromine bond. And thinking about my total transition state has a -1 charge. So that -1 charge will be dispersed on both my nucleophile and my leaving group. All right. So what do we learn by observing this concerted reaction mechanism? One of the obvious conclusions we can make is that my nucleophile, or my OH group in this case, will always be on the different side comparing to my leaving group. Or by simple observing the transition state structure, we can derive that a reaction or a nucleophilic substitution reaction following the SN2 reaction mechanism must lead to inversion of stereo configuration. Now, in this case, we're not looking at a chiral molecule, so it doesn't matter. But if we are looking at a chiral molecule by replacing the hydrogen with other substitutions, you will expect an inversion of the stereochemistry. Yes?
You said the charge is -1. Is that what that on a very top is?
Right, so in both cases, on the left and right-hand side, we have -1 charge. So don't think about them as actual numeric number. They are all partial charges that add up to be -1. The actual number of the partial charge is beyond our level.
Oh, so what if we were to draw that on a test, we don't need to include that symbol that's on the top there?
Right, so these are partial negative charges.
I think she means double dagger.
Oh, this one?
Yeah.
That one just hinting that is a transition state. All right, so that's the SN2 reaction mechanism. Alternatively, this nucleophilic substitution reaction undergoes the SN1 reaction mechanism. And in the SN1 reaction mechanism, it's a stepwise process. So if we draw it out we're looking at a process of first, the dissociation of a polar covalent bond. So in this case, if we're looking at the carbon and the bromine, where my bromine is my leaving group, we're dissociating this polar covalent bond into a carbocation intermediate. And Br minus. But in this case, my Br minus is not acting as my nucleophile. It's my water acting as a nucleophile, or a methanol acting as a nucleophile. So that's a nucleophilic electrophilic addition. My Br minus just hanging around. And then the last step will be the deprotonation by another solvent molecule. To form my final product. And to balance it, we'll end up getting HBr as my final product, side product. So overall, if we look at the energy profile, what do we have? We have a three-step process. The first step is coming from here. We're talking about the dissociation of my carbon-bromine bond to form my carbocation intermediate. So in the first step, which is the formation of the carbocation intermediate, or leaving group leaves, so that process is my rate determining step. In this case, if we look at the actual transition state, that looks like 3CH3 to a carbon, and we have a partially breaking carbon-Br bond. And we're forming a carbocation intermediate and a Br minus as our product. So you could expect like partial negative charge on the Br, partial positive charge on the carbon in that transition state. And again, this first step is our rate determining step. The next step, which is the methanol comes in and reacting with the carbocation, also have a activation energy barrier, but since my second step is a much faster step, it does not contribute to the overall rate of the reaction. So when we're comparing the two mechanisms, we're typically comparing only the first step with the concerted SN2 transition state. Okay, questions?
What causes the leaving group to leave? Why is the bromine ion being broken off of the...
So the way to think about it is this process is a uphill process to form the carbocation intermediate, but the formation of the final product is thermodynamically favorable. Again, the reason behind it is my carbon-bromine bond is a much weaker bond comparing to the carbon-oxygen bond that we're forming at the end, right? So overall, if we give the reaction enough time at certain temperature, as long as this activation energy is available at room temperature or we heat it up, there will be some carbon-bromine bond breaking taking place. Whether or not it will stay here that's out of our question. It's like eventually we have the reaction taking place and we're forming the more stable product at the very end. So the fact that our final product is more favorable comparing to my starting material, that's called the driving force of the reaction.
Okay, thank you.
Okay, question.
Well, determines if it does the SN2 or the SN1.
We'll talk about that in next slide. All right, so here is a quick introduction into the question is what is SN2 reaction mechanism and what is SN1 reaction mechanism? Remember in the SN2 mechanism, we derived that the stereochemistry must be flipped in the SN2 reaction mechanism because your nucleophile approaches the carbon center from the opposite side of the leaving group. If we do the same kind of analysis on my SN1 reaction mechanism, we expect the SN1 reaction to be not stereo-specific, because when we're forming the new carbon oxygen bond in the second step, in this case, we're looking at the nucleophilic addition onto a carbocation intermediate. And like what we discussed before, right? So the carbocation intermediate itself is a planar molecule. So when my nucleophile, in this case methanol, comes in, it doesn't matter which phase it attacks. So my SN1 mechanism is not a stereo-specific mechanism. Right? So these are the information we get by observing the reaction mechanism. And now let's move to the question, right? Now we know what does SN1 mechanism and SN2 mechanism mean. What are the factors contributing why, like given a known reaction, an unknown reaction, how do you predict whether or not the reaction proceeds via SN1 mechanism or SN2 mechanism? And let's look at it one by one. So, like the acid-base chemistry, there are several things that we care about the competing SN1, SN2 reaction mechanism, involving like structure of the Rx, the steric and electronic factor. And we'll review the stereochemistry that we just discussed and the effect of the solvent, and well, also potentially talking about the nucleophilicity and leaving group ability and try to clear out those terminologies. I'll see how fast I go. Let's get started talking about the structure of Rx. Right, so when we're talking about the SN1 reaction, again, what are we talking about? Is this R3 carbon, and you have a group with a leaving group. In the rate limiting step of your SN1 reaction, you're forming a carbocation intermediate, and the leaving group leaves. So in this case, because we're forming a carbocation intermediate, as we were discussed before, we have the same trend for stability of the carbocation intermediate and the same challenge. Remember when we were talking about the acid catalyzed hydration of alkene, whenever we're forming a free carbocation, we have two pieces of information. First, the tertiary carbocation is more stable than secondary, than primary. Right, so depending on how much substitution you have on your substrate, on your tetravalent carbon, more substitution you have, more likely it undergoes the SN1 reaction mechanism to form the more stable carbocation intermediate. Secondly, because the SN1 mechanism forms the free carbocation intermediate, we also have potential carbocation rearrangement. All right, so two pieces of information coming from factors that's governing the SN1 reaction mechanism. We will always want to form the more stable carbocation, tertiary over secondary over primary. Also, when we're looking at the free carbocation, keep in mind the carbocation rearrangement can take place. Alternatively, when we're looking at the SN2 reaction, now the SN2 reaction mechanism does not form a free carbocation intermediate. So the stability of the carbocation has little effect on the SN2 reaction rate. Alternatively, the steric factor plays a much greater role in the SN2 reactions. Or the other way to put it is depending on how easy the nucleophile can approach the tetravalent carbon center, we have faster SN2 rate if the nucleophile can more easily access the tetravalent carbon center. For example, in this case, if we look at a primary carbon center, meaning you have like a CH3 on it, in this case, when we're looking at the actual van der Waals surface, or what does these atoms look like? I mean, when we draw it on paper, it looks all similar sizes, but in reality, your hydrogen, your carbon, your methyl group, your bromine, they all occupy a certain space in our 3D space. They all occupy that area. So whenever you have like a smaller group, like in this case, the carbon center, the OH minus or your nucleophile is easier to access the tetravalent carbon or the black area. Alternatively, if we're adding more and more substitution onto the tetravalent carbon, we're making that carbon center more and more shielded from the attack of the nucleophile. The extreme one will be like a terbutyl bromide. So in this case, you have 3 methyl group around that carbon center. So in this case, because my carbon center is being sterically blocked by these substitutions, the nucleophile cannot come in. And consequently, it does not undergo the SN2 reaction mechanism. In comparison, like if we think about it, actually works towards each other, right? When we're looking at these, like for example, the terbutyl bromide, this tells me my SN2 reaction mechanism is gonna have a much higher barrier because of the steric disfavorance. So in this case, if we draw it on the energy diagram between your reactant and products, actually, let me draw this on the board. It might be easier. So if we draw this on the board, so considering the terbutyl one, so we're looking at a CH3, 3 of them, carbon, Br. My starting material is the same for both mechanisms. We're looking at CH3, carbon, Br, and then a OH minus. The product is also the same for both reaction mechanisms. All right. So in this case, because my carbon center is highly sterically congested, we're looking at a very high barrier for my SN2 transition state, and that looks like my OH minus trying to form a bond, a partial bond between my fully substituted carbon while breaking the Br bonds. So my SN2 is going to be very high in energy because of the steric disfavorance. Alternatively, if we look at the potential SN1 reaction mechanism, in which we're breaking a carbon-bromine bond to form the carbocation intermediate, via the SN1 reaction mechanism. So because my carbocation intermediate is stable, my first transition state to break that CBr bond will also be lowering energy. All right, so taking together, when we're putting them on the potential energy surface, and then we have the second step that goes to the product that we don't get. So we're comparing these two energy differences, talking about whether or not you're having SN1 mechanism or the SN2 mechanism. In reality, our molecules doesn't care how do we draw them on the board. It's more like you have these two potential things can taking place, leading to the thermodynamic more stable product. Whichever is lowering energy will take place. If we look at the other extreme, which is thinking about my ethyl bromide. Now, instead of having these terbutyl groups, what we have is the ethyl bromide. So on the carbon, I have a CH3, and then hydrogen, hydrogen, and Br. Right, so when we're looking at this case, we're looking at a different scenario. That is, if we're looking at, again, the energy versus my reaction coordinates, the starting material is the same, but now, because my carbon center is less sterically hindered, or if we look at the other extreme, let me make it a methyl one. But let's look at the other extreme. Now, my carbon center is less sterically hindered. My SN2 transition state will be way more favorable. Alternatively, in this case, if we're breaking the carbon-bromine bond, we'll be forming a methyl carbocation, which is highly unfavorable. And consequently, the transition state before that, for my SN1 substitution to take place, will be way higher in energy. Right? So at the end of the day, if we're looking at a methyl bromide, it must undergo the SN2 mechanism because, well, electronically, we're disfavoring SN1, sterically we're favoring SN2. So these two factors in general will work towards each other when we're talking about the SN1 and SN2 reaction mechanisms. When you have like a methyl or a primary carbon halogen bond, it's very likely it will undergo the SN2 mechanism. If you have a secondary or tertiary, it's more likely to undergo the SN1 mechanism. All right. Yes?
So is that like pretty much common enough to say, okay, it's a secondary or tertiary, so it's this, versus like a methyl or primary SN?
Well, so these two in the middle are are more complicated because you will be looking at other factors. But if we're looking at a tertiary or a methyl, then it's pretty set. All right, so tertiary nearly always undergo SN1, methyl always undergo SN2. Now, in between, when you have primary and secondary, other factors also contribute. And let's look at what are these other factors. Well, the stereochemistry we sort of mentioned already in previous cases, talking what are the outcomes from the SN2 and SN1 mechanism. So I'm going to quickly skip it here because we just discussed. The next factor that is very important is solvent. So it's a quick review. When we're talking about solvent, so in Gen Chem, you learn that solvent can be polar or nonpolar depending on their dielectric constant. And dielectric constant is a measure of the solvent's ability to insulate opposite charges from one another. So in this case, like S represents like solvent, and when you have like sodium and chloride, the solvent will be able to separate them from one another. So a polar solvent will have larger dielectric constant, and a nonpolar solvent will have a smaller dielectric constant. In organic chemistry, because we talk about hydrogen transfer or proton transfer a lot, the other factor of the solvent, or another dimensionality describing the solvent, is protic versus aprotic. So a protic solvent means the solvent can act as a hydrogen bond donor. Can be water, ethanol, acetic acid, or methanol. Right? So as long as your water has the ability to undergo hydrogen bond donor and acceptor, it's called protic solvent. Or you can have aprotic solvent, or a solvent that cannot serve as a hydrogen bond donor. Can benzene, hexene, DMSO, DMF. So these are aprotic solvents. Note that aprotic solvent can also be polar solvent. So for example, in this case, when we're looking at DMSO and also DMF, like you can write the internal dipole moment. For example, DMSO, you know that your sulfur is less electron negative than oxygen, so we have an overall dipole. So my DMSO is a polar but aprotic solvent. Right, same applies to DMF. We have like this one is partial positive, partial negative nitrogen, partial positive carbon, partial positive carbon, partial negative oxygen. So overall, in your DMF, you have an internal dipole moment. So how does the solvent affect the rate of my SN2 versus SN1 reactions? So let's think about it. First, let's look at SN2. Again, these are the mechanism we went over, talking about that in the starting material, your charges are fully separated, or your nucleophile is negatively charged. In your product, your leaving group is negatively charged. However, in the transition state, the negative charge is more like delocalized in the transition state on both the nucleophile and the leaving group. So the logic comes to say, like, if we have weaker solvation of the nucleophile, it takes less energy to remove it from the solvation shell. Right, so in the starting material, we want the nucleophile to be able to attack the carbon center. So if your nucleophile is being highly surrounded by your solvent, it's less likely to remove your nucleophile from that solvent cage. With me so far? So that is why we say that the SN2 reaction mechanism typically favors polar aprotic solvent. So the aprotic solvent does not form hydrogen bonds with your nucleophile, and hence it is easier to remove the nucleophile from the solvent cage and promote the SN2 reaction mechanism. We'll talk about SN1 very soon.
Just clarifying, if there is an overall dipole moment, it's always going to be aprotic.
What's that?
If the solvent has an overall dipole moment, it's always going to be aprotic. Is that what you said?
Well, so the protic and aprotic are two different concepts. Protic and aprotic describes whether or not the solvent can act as a hydrogen bond donor. The polar versus nonpolar describes whether or not the molecule has an internal dipole moment. I don't want to say yes to that question because maybe there is a special case that your solvent can act as a hydrogen bond donor and yet does not have an internal dipole moment. Very unlikely, but it's two different dimensionalities. Do not mix them. So coming back to the rate of our SN2, the take-home message here is that the polar aprotic solvent are better solvents for SN2 reaction mechanisms. Alternatively, what about SN1? So SN2 doesn't want the polars, the protic solvent or the hydrogen bond donor. Alternatively, if we're looking at the solvent of SN1, well, so keep in mind that the key rate determining step of SN1 reaction is the formation of my carbocation. So having the protic polar solvent or my water or methanol in this case, they'll be able to better stabilize the iron pair that are being generated in the process of the formation of my carbocation intermediate. So polar protic solvents like H2O or methanol, these are better solvents for SN1 reaction mechanism. All right. And I have about 5 minutes left. Before we finish our today's lecture, I want to quickly emphasize the importance of these terminologies. So far we went over several similar terms that are inherently different. They're related in strength, but they're conceptually different. These are basicity, nucleophilicity, and leaving group ability. So basicity here is specified for the Bronsted acid-base reaction. So here's the difference. When we're talking about nucleophilicity, it is a kinetic property measured by the rate at which a nucleophile causes a nucleophilic substitution reaction. So it is, when we're talking about nucleophilicity, this is a sole kinetic parameter talking about what is the rate of this nucleophilic substitution reaction. And I highlighted SN2 here because in SN1 reaction, the nucleophile is not involved in the rate determining step. All right, so the nucleophilicity is deeply related to the rate of an SN2 reaction. Alternatively, when we're talking about basicity, we're talking about a thermodynamic property that's telling us the position of the equilibrium in a Bronsted acid-base reaction. Right, so in the Bronsted acid-base, you have a base, you have a general acid, HA, and well, your base grabs a proton and forms your conjugate acid and base. So basicity describes the overall thermodynamics of this Bronsted acid-base reaction. So they are related, but they are conceptually different things. As we were saying, like typically the base and the basicity and nucleophilicity of a group will correlate with each other, but they are conceptually different things. In addition, we also have the leaving group ability, which is applicable in both SN1 and SN2 reaction, right? So if we look at the transition state here, in your SN2, your leaving group is partially leave, and in your SN1, well, it's leaving group leave. So in both cases, the leaving group ability will contribute to the rate of your SN1 or SN2 reaction mechanisms. On the other hand, the thermodynamic driving force is also part of the reason we care about the stability of the leaving group. So in the product here, we're forming Br minus as our product. So the overall driving force is also determined by the stability of the anionic leaving group or the leaving group itself. So in this case, when we're talking about leaving group ability, we're considering leaving group ability being both a kinetic and thermodynamic factors. Where in previous cases, nucleophilicity only kinetic, and then basicity only thermodynamics. Leaving group ability, sort of both. And in here, well, we're saying the strength of the leaving group. Typically, the larger group will be easier to leave because their size are larger, and it's easier to be polarized them in the transition state. And the more stable the anion, the more likely it will leave. So the conjugate base of a strong acid will likely to be a good leaving group. So that's why we have like iodine is a better leaving group than bromine, than chlorine, than fluorine. All right. And at the very end, the rest of it, the nucleophilicity trend, these basically correlates to the trend of our basicity. So I recommend you use this part as a refreshment on things we discussed when we were talking about the basicity of Bronsted acid-base reaction. All right, and your final exam will cut from like right here. All right, so everything Dr. Marsh discussed with you on Wednesday, I'm not gonna test you on that, but those will be essential for your 30B. So I still highly recommend you come to the lecture and listen to it. I've also posted the lecture notes for rest of the elimination and also the competing mechanism in our Brewing Learn lecture. All right, I'll see you around.